The moon has been hanging in the sky for so long that it feels like it was always there, a fixed point, something that simply exists, the way the sun exists, the way the ocean exists. Most people never stop to ask where it actually came from. The honest answer is violent. The moon was not always there. Earth once had no moon at all, and the event that created it was so destructive that for a brief period, it nearly ended the planet before human history had any chance to begin. This is Beyond the Cosmos. If questions like this are why you are here, subscribe and stay with us. This one starts with a collision and ends with the reason you exist at all. To understand how the moon formed, you have to go back to the very early solar system, roughly 4.5 billion years ago. At that time, Earth was young, still partially molten, still settling into the planet it would eventually become. The solar system itself was a chaotic place. The sun had ignited. The planets were forming out of a swirling disk of gas and dust. But the process of planet formation was not clean. It was a violent sorting process, with large objects colliding, merging, and sometimes being destroyed entirely. Earth was not the only large body occupying its orbital neighborhood. According to the leading scientific model, there was another object roughly the size of Mars, sharing a similar orbit around the Sun. Scientists have given this hypothetical world a name, Theia, after the Greek Titan who, in mythology, was the mother of the moon goddess Selene. It is a fitting name, because what happened next gave birth to the moon in the most literal sense. At some point, the orbits of Earth and Theia intersected, not at a grazing angle, and not in a slow, gentle drift. The two bodies collided directly, at a glancing angle, with a violence that is almost impossible to translate into ordinary language. This is known as the giant impact hypothesis, and it is currently the most widely accepted explanation for how the moon formed. The energy released in that collision dwarfs anything that has ever happened on Earth since. Modern simulations suggest the impact vaporized a significant portion of both Theia and Earth's outer layers, throwing an enormous quantity of molten and vaporized rock into orbit around the planet. Earth itself was likely reshaped by the impact, its rotation altered, its early crust melted and reformed. What happened next took place remarkably fast by geological standards. The debris thrown into orbit, a glowing ring of vaporized rock and molten material, began to cool and clump together under its own gravity. Within a period that some models estimate at less than a century, and almost certainly within no more than a few thousand years, that debris ring had coalesced into a single object, the moon. That timescale is worth sitting with for a moment. An object more than 3,000 kilometers across, large enough to dominate the night sky for the rest of Earth's history, assembled itself out of impact debris in less time than many human civilizations have existed. It was not a slow accumulation over millions of years. It was fast, hot, and immediate. The evidence supporting this version of events comes from several independent directions, and it is worth understanding why scientists trust it as strongly as they do. The first major clue comes from the rocks themselves. When astronauts brought lunar samples back to Earth during the Apollo missions, scientists were able to study the chemical composition of the moon directly for the first time. What they found was striking. The isotopic signatures in lunar rock, specific ratios of oxygen isotopes that vary depending on where in the solar system a body formed, are nearly identical to those found in rocks from Earth. If the moon had formed independently elsewhere in the solar system and had simply been captured by Earth's gravity later on, its isotopic fingerprint would look different. Instead, the moon's chemistry tells a story of shared origin, of material that came from the same source as Earth itself. The second clue involves what is missing from the moon, rather than what is present. The lunar samples are strikingly depleted in volatile elements, the kinds of elements and compounds that evaporate easily at high temperatures. Things like water and certain metals that boil away under intense heat. This depletion makes sense if the moon formed from material that was vaporized in an enormous collision, and then cooled and reassembled in orbit. The third clue is the moon's relatively small iron core. Earth has a large, dense iron core that makes up a significant fraction of the planet's total mass. The moon's core, by comparison, is proportionally tiny. The giant impact hypothesis explains this elegantly. By the time the collision occurred, Earth had already mostly finished forming its core. That is why the moon ended up as a relatively rocky world with a small core, while Earth kept the bulk of the original iron for itself. Together, these pieces of evidence form a remarkably consistent picture, not a perfect one. There are still open questions, including exactly how much of the moon's material came from Theia versus Earth, and why the isotopic match between Earth and moon rocks is as close as it is. Science continues to refine the details, but the broad outline, a catastrophic collision followed by rapid coalescence, has held up against decades of scrutiny. But the more important question is why any of this matters. Why does an event that happened 4.5 billion years ago have any bearing on anything happening on Earth today? The answer is that the moon did not just appear in the sky and remain a passive bystander. It fundamentally shaped the conditions that allowed complex life to exist on this planet at all. The first and most significant effect involves Earth's axial tilt. Every planet rotates on a tilted axis relative to its orbital plane, and that tilt is what gives us seasons. But without something to stabilize it, a planet's tilt can drift chaotically over time, swinging through extreme variations driven by the gravitational tug of other planets in the solar system. Mars, which has no large moon, demonstrates this problem directly. Its axial tilt is believed to have varied wildly over millions of years, swinging by tens of degrees, which would produce catastrophic and unpredictable climate shifts if anything were trying to survive there long term. Earth's tilt, by contrast, is remarkably stable, wobbling by only about plus or minus 1 degree over very long timescales. The reason is the moon. Its gravitational pull acts like a stabilizing hand on Earth's rotation, keeping the tilt locked within a narrow, predictable range. That stability is what gives Earth consistent, predictable seasons. The second major effect is tidal. The moon's gravity pulls on Earth's oceans, creating the rise and fall of tides that happen twice a day in most coastal regions. This sounds like a minor curiosity, but its biological implications are significant. Tidal zones, the regions of coastline that are alternately submerged and exposed as the tide rises and falls, are believed by many scientists to have played an important role in the early evolution of life. These zones create a uniquely dynamic environment, with organisms exposed to alternating wet and dry conditions, concentrated pools of nutrients, and constantly shifting chemical gradients. Some researchers argue that this environment may have provided exactly the kind of varied, high-energy conditions needed to help drive the earliest chemical steps toward life, and later, to help push early marine organisms toward adapting to life on land. The third effect is more subtle, but no less important. The moon's gravitational interaction with Earth is gradually slowing our planet's rotation. Billions of years ago, a day on Earth was significantly shorter than 24 hours, possibly as short as 6 hours not long after the moon's formation. Over billions of years, the moon's gravity has acted like a brake, transferring rotational energy away from Earth and gradually lengthening the day. If this changed how you see the moon tonight, subscribe to Beyond the Cosmos. Like the video, turn on notifications, and leave a comment telling me whether you think Earth could have supported complex life without it. I read every single one.